So it's been a while since we did Smith Chart 101, so I'm going to do a little bit of review. So why do I want to use the Smith chart? Because antennas are confusing and they're bloody magic, and explaining them is difficult. And you don't have to go through what we're going to look at today is a lot easier done in the software, and I'll show you the software at the end of this. But actually working the Smith chart helps you to picture in your mind what it is that's going on and what's happening. And so I've been real surprised about the things that I've learned going through figuring out how to work these Smith charts. But they do illustrate complex entities in a manner that's more easily understandable because it presents it as information, not just a bunch of noise. We talked a little bit about complex numbers. Some of the complex values that we'll be talking about are resistance, reactance, and impedance, where impedance is a combination of the resistance and the reactance in a two-dimensional number. Another one, and we're going to get into this one today, real or applied power. That's the power that actually does the work, and it's analogous to the resistance. Then there's reactive power. That's power that sometimes called circulating power because it goes back and forth, but it doesn't do anything meaningful other than increase losses, which I suppose that you could consider that meaningful. And then apparent power, well, that's kind of a combination of the real power and reactive power together. And I've got this cute little illustration that I think is fairly self-explanatory, particularly if the glass is full of German beer. But just think of the liquid part as the real part, the foam as the reactive part, and then the impedance, or if you will, the well, I guess I could go on brain dead. Think of the impedance as the combination of the reactance and resistance. All right. Remember we talked about the magic number, aka the operator J. What number multiplied times itself equals -1? Good one. It's an imaginary number. The funny thing is that utilizing this operator J, treating it like the square root of -1, which doesn't exist, but then plugging it into algebra, it works. So it was a pretty neat invention, and its primary purpose is to display this complex number in a two-dimensional grid. All right, so back to where I was. The object of operator J is to add a little mathematics to displaying this complex number on a two-dimensional grid. And everything with the complex number exists on the right-hand side of this grid. Matt had somebody tell him the other day that all they did for the Smith chart was they took this right-hand side of the grid and they wrapped it around 180 degrees and turned it into a circle. And that's really true. Now, in this particular case, this number, two-dimensional, he's got magnitude and he's got phase. But essentially, if I look at this, I've got 1, 2, 3, 4, 5 steps along the x-axis. That's what we call the real axis, or in this case, resistive axis. So that's the first part of our number. The second one, if we look up the vertical side, 1, 2, 3, 4, I've got 4 steps up the vertical side. So now this number is displayed as 5 plus operator J 4. That's this here in the bottom left-hand corner. Now, if I go through the process of converting it to polar coordinates, the magnitude is 6.4, and this phase angle is 39 degrees. Well, the magnitude happens to be this R right here, the hypotenuse of this right triangle. And the phase angle, it uses the Greek letter theta, is this angle right here. And you'll find tonight that particular phase angle is important. So since we're doing this based on a right triangle, we can use the Pythagorean theorem to manipulate these numbers. A, the vertical part, is the X, or the reactive imaginary part. B is the resistive or real part. C is the impedance, or the complex part. And these four formulas that I'm bringing up are four formulas that you really need to use when you take your extra exam. But essentially, they're just manipulating this complex number. Now, here's the nice, interesting part. We really need to know the sign of operator JX. So we can get it from our vector network analyzer, aka our antenna analyzer. But most of those antenna analyzers that'll do it, we can't afford. They're pretty expensive. Now, the rig expert jobs, which are more or less in our price range, do give us the sign. So that's an important point. But most of the rest of them do not. So how do we get it? This is a screenshot from my Comet CAA 500, and if you look at it, I'm at 7.064 megahertz, and it gives me a resistance. This, by the way, is my my antenna here, my off-center fed antenna. It tells me the resistance is 38 ohms, and the reactance is 13 ohms. Now, there's no sign. How do I get the sign? Well, it is doable, but you got to pay attention to a little bit of mathematics. All right, so there's two types of reactants. There's capacitive reactants and there's inductive reactants. They both introduce a phase shift. The inductive introduces a positive phase shift. That is, the current lags, the voltage leads. The capacitive has just the opposite. It has current leading and voltage lagging. So it's a negative phase shift, or a negative minus operator J. So take a look at this equation for inductive reactance. The reactance for the inductor is 2 times pi, so that would be 2 times half a circle, so that would be a complete circle, times the frequency, times the inductance. So think about this for a second. If I increase the frequency, what happens to the inductive reactance? Right, it goes up. If I decrease the frequency, the inductive reactance goes down. Capacitive reactance is just the inverse of that. So it's the inverse of 2 pi f times the capacitance. So if I increase the frequency, I'm going to decrease the capacitive reactance. So I can use that little secret to get the sign off of my CAA 500 antenna analyzer. One other thing, this is important. If I get my capacitive and inductive reactance equal, they cancel each other out and the circuit goes resonant. More on that at another time. So let's go back to my screenshot. I've got 7.064 megahertz. I've got an R of 38 and an X of 13. So what happens if I slowly start turning up the frequency? Here I was able to stop it at 7109 kilohertz. What did I do to X? It went up. You got to do this very slowly and very carefully, because if you're near resonance, that sign can change at the drop of a hat. I mean at the blink of an eye. So you have to watch it very carefully. But this one I was able to confirm that it's going up. So since it's going up, this particular one is R of 42 plus J 18. So you can always get that. Now, this is just kind of a quickie overview of the chart that we're going to be working with. Notice right here in the center, we call it prime center, it's 1.0 plus J0. So this line that I'm walking across here is the real line, or the resistance line. These curves off here to the side are reactive. On the top side, it's positive reactive. On the bottom side, it's negative reactive or capacitive. So I've got inductive up here. I've got capacitive down here. So the imaginary part is here. The resistive part, the real part, is here. So we're going to take and normalize this. Most of the time we're working with 50 ohm coax. So to normalize this, you would take and divide your coax impedance by 50, and it should come out to something very close to 1.0 plus J0. And so that's prime center. Then when I get a measured impedance, in this case a measured impedance of 50 plus J100, if I divide that complex number by 50, I will get 1 plus J2. And I'm going to plot that over here on this side of the chart. Then the next thing I'm going to do is take a compass from here, reach out to this point with the other side of the compass, and I'm going to draw a circle that is a constant SWR circuit. So anywhere along that line, the SWR will be the same. Prime center represents an SWR of 1.0 to 1. And so it's a circle with 0 radius. All right, now I want to talk about what we ignored the last time, because we went through and figured out what the actual impedance was at a given frequency at the antenna. But what we didn't pay attention to was line losses and what they do to us. At the lower frequencies, they very, very well may be negligible, especially if you're using low loss or short feed line. Or if you take Dave's case, Dave Martin's case, he's using this window line. It's real low loss. But that actually starts to increase pretty dramatically as the frequency goes up. And later, after we're done with most of the presentation, I'll show you some great charts that show different attenuations as frequency goes up. But because of these losses, the SWR is not constant along the length of the line. It actually goes down the longer the line gets as you progress away from the load. All right. So, little summary. We did this last week. You're going to normalize and plot a line input or a load impedance and construct a constant SWR circle. Since the characteristic impedance equals 50, we divide that impedance by 50 to get it to 1.0 and J0. Then we take and plot the measured impedance. In this case, we're measuring the impedance at our radio, and here we're measuring 50 plus J35. That's what came off of the antenna analyzer. So we plot that at this point right here. Then we draw a circle around it. So everywhere on this circle is the exact same SWR, and then we draw a line from prime center through our impedance and up off to the circles here. The circles represent phase shift from 0, and there's two of these circles. One is going towards the load, which is the antenna. The other one is going towards the generator, which is the transmitter. Okay, so we now need to apply the line length to the wavelength scale. One of the things that was given here, let me step back over here. If you look in the upper left-hand corner, among the givens in this case is 50 ohm coax. It's 0.282 wavelengths long. It has 1 dB of inherent attenuation based on its length. The measured line input impedance is 60 plus J35. I think I said 50, but it's 60 plus J35. That normalizes to 1.2 plus J0.7. and that's how we got it to this point right here. Sorry, I missed that. So now what we're going to try and determine today is what is the SWR at the input, what is the SWR at the load, which is the antenna, and what is the actual load impedance, taking into account the losses in the line. Okay, so we need to apply the line length to the wavelength scale, which we've done. One of the things that we've done, so we cross the wavelength scale, and it starts at 0.328 toward the load crossing. Now we're going toward the load because we got our base number, our starting point, off of the generator. So we went to the radio. At the radio end, that's where we measured the SWR. So what I've got to do then is I've got to add the length of the line to the starting point, which is 0.328. Well, that gives me a total number of 0.610 wavelengths. Trouble is, there's only 1/2 a wavelength all the way around the chart. So, and the reason for that is that everything is identical every 1/2 a wavelength. So there's no point in charting more than 1/2 wavelength. So what I need to do then is simply subtract a 1/2 a wavelength from that 0.610, and it gives me 0.110. So now I need to locate 0.110 on the toward load scale and draw a radial line from there to prime center. So here was the 0.328. I added the 0.282 to it, and I subtract the 0.5 wavelengths, and I end up here at 0.110 on the toward the load scale, which is the second one in. So now I just draw this line from prime center out. And right here, where I'm touching it with my arrow, that's going to be initially my, I'm sorry, I'm going to brain dead, guys. That will initially be my impedance at the antenna, but not taking into account the effect of the line. We'll do that next. So we want to transfer the radius of that SWR circle to both SWR and attenuation scales at the bottom of the graph. So here's the graph. I'm going to blow it up a little bit. You know, it's my regular graph up here at the top. Here's the graph that we're looking at here at the bottom. And I've actually highlighted SWR, that's coming across the top line here, all the way to prime center, which is right here. Then the attenuation in dB it's also sometimes called the step attenuation or the step dB scale. It's over here on the right, and it's listed also in dB. So if I'm going to take this distance from prime center to the SWR circle, bring my compass back down here to prime center, and I'm going to swipe at this point and at this point. So I see that my SWR is somewhere in the neighborhood of 1.95, and my attenuation is falling somewhere on the scale at 5. So between 5 and 4 is 1 dB, between 5 and 7 is 2 dB, so there'd be 6 right about there. Since we know there's a matched loss on this line of 1 dB, so we strike a new radius 1 dB toward the load from the mark made in this previous step. And I'll show you that. Then we want to transfer this radius to the main chart, creating a new SWR circle, where this circle crosses the line from 110 toward the load, and prime center is the load impedance. So back down here, now I will blow this up. Okay, so you see here, I've started out right here with this is where I was on the step attenuation or the step dB. I've got 1 dB of known attenuation in that length of cable. So I'm going to go towards the load, 1 dB, and strike a new radius. So my hand is pointing at prime center over here to the number 4. That's my 1 dB. So now I'm going to take that 1 dB, that new radius, and I'm going to take my compass and draw this second outlying circle out here. Where this line crosses that circle, that's going to be the normalized, corrected impedance at my antenna feed point. Not at the radio, but actually at the antenna feed point. And that comes out to, looks like 0.6 minus J, let's see, I think that's 0.68 minus J 0.6. Okay, so now we're back to where we were. All right, now, you'll notice here I've got a single circle that's the same all the way around. But that's not really what's truly happening. We can do that because the only thing that really matters is where it crosses our line right here. That's the one that we care about. But if we were to really plot this thing step by step by step, it would be a spiral going around, not a single circle. But there's what we're going to work with now, is this point right here. Okay, so in summary, again, we normalize and plot a line input or load impedance and construct a constant SWR circle. Apply the line length to the wavelength scale. Determine the attenuation or loss if required by means of a second SWR circle. Then we're going to read the normalized load or input impedance and convert it to impedance in ohms. Now we're going to convert that impedance that we found in normalized mode into its actual number. We're simply going to multiply it times the characteristic impedance of the coax, which is 50 ohms. So we'll multiply it times 50 to get the number. So the SWR at the input or at the transmitter is a measured 1.9. The SWR at the load or the antenna is 2.3. Oops. How did that happen? It's worse than I thought it was. The only thing that's happened to me here is that I fooled my radio into thinking that the interface is better than it really is. So the radio is keeping its power output up. That is a positive thing, but he's not necessarily sending that much more energy out the antenna. In fact, he may not be sending any more energy out the antenna. The load impedance on this is 32.5 minus J30. That equals a magnitude of 44.23 and a phase of 42.7 degrees. There's where the trouble comes in. We'll get to that here directly. All right, something I forgot to point out. I'm going to blow this up again. Sorry, I need to go back and do this because this was an important point. I think this was something Dave was trying to mention to me at one point, and I didn't catch it. But I did this time. Okay, if you look at this second line over here, all right, I've got attenuation. This is my step dB attenuation up here on the top. And a line immediately underneath it is a standing wave loss coefficient. What that coefficient tells us is how much to multiply that 1 dB of intrinsic loss that I've got in my coax by this amount. Well, at one end it's 1.2, at the other end it's 1.4, so average it. Our standing wave loss coefficient is 1.3. So since I've got 1 dB of intrinsic loss in that cable, because of the standing waves, because of the higher voltages and the higher currents with the standing waves, I actually get more what we call I²R and dielectric losses. Now my losses on that line are actually 1.3 dB, not 1. That can make a bigger difference than it did before. All right. Back to where I was. Sorry about forgetting that. All right. For starters, the feed line losses are greater than the 1 dB we used for this example. The SWR loss coefficient shows that those losses are greater than 30% more than anticipated. And SWR losses are greater than what we would see from our antenna analyzer at the input. Okay, so now it's time for a little bit of arithmetic. Hope you guys have got your calculators or slide rules with you. So I went to the trouble of drawing a graphic here. This is your transceiver, transmitter going out. I've got a feed line that's nominally 50 plus J0 ohms, characteristic impedance. I've got a load. Pretend this is a resistance here. And I've got a capacitor across that load. So I've got 32.5 ohms of resistance and minus 30 ohms of capacitive reactance over here. So the feed line losses, including the standing wave loss coefficient, is 1.35 dB. All right, dB is when we're talking about power, and that's what we're really dealing with here is power reflected back towards the radio. dB is equal to 10 times the log of the ratio of the two powers. So I've got forward power going from the radio to the load. It hits that load and realizes that that load is a different impedance than the feed line, so some of that gets reflected back the other direction. Where does it go? Well, some of it gets lost as heat in the coax. The rest of it ends up getting lost as heat in the transmitter. It's possible that there's if you will, a mismatch here at the transmitter, and so some of it could get reflected back to the load and then back and forth and back and forth. But it'll be not nearly as much doing that, because if there's a mismatch here, you're going to have less of it getting on the line in the first place. So everything we're going to evaluate is going to assume that the connection from the transmitter to the coax or the feed line is pretty much ideal. And it certainly is. Even with the old tube radios, we're actually adjusting the loading. So we're tuning to that. So the feed line losses here then, in dB, since I know it's 1.35 dB, if I want to find out how much power is being reflected, then what I really need to do is get this P1 and P2 ratio and find out which one of these, since I know that P1 is 100 watts and dB is 1.35, then solving for P2, I get 73 watts. So that means that if I've got 100 watts here, only 73 watts are getting into the antenna. 27 watts is going back towards your radio. That's with an SWR of 2.3. All right. SWR itself, or an SWR of 2.3, means that 15.5% of the forward power is reflected back. So with 73 watts arriving at the antenna, only 61.9 watts gets to the antenna. The rest is reflected back to the transmitter. You know, I've got this wrong here. I only got 73 watts to the antenna because of the feed line loss. Sorry. So I got 73 watts arriving at the load, and then I've got 15% of that, roughly, being reflected back, or now I've only got 62 watts at the load. All right. Now we get to the phase angle. This is the one that bites, and it bites really hard. It's called power factor. Power factor is essentially that ratio of apparent power, or real power to apparent power. Remember the glass of beer. The foam on top was reactive, the liquid beer was the real, and the combination of the two is what we call apparent power. It's also the magnitude of the complex number. Well, power factor is determined by the load, not by the transmitter, not by the generator. The load determines what the power factor is going to be. So in this particular case, the power factor is the cosine of theta. That's that angle between the hypotenuse and the real portion of the right triangle. The cosine of 44, or the cosine of 42.7 degrees is 0.737. So of the 61.9 watts that gets to the antenna, only 45.65 watts is real or applied power. That's the only power that radiates. Real power is the only power that does any work. And in our case, work is we radiate. Reactive power does not radiate. So now, all of a sudden, because of that wonderful measured 1.9 SWR that I got at my radio, less than half of the 100 watts my radio is putting out, it's actually getting on the antenna. And I'm not dealing yet with the antenna's efficiency. I'm dealing only with the efficiency of the system itself. It's below 50% just getting to the antenna. Okay, so let's, how did I get there? Just in summary, I got 100 watts output from the transmitter. I've got 27 watts of feed line loss from the transmitter to the load. I've got 11.1 watts of reflected power coming back, and then I've got 17.44. I should put VA in there because that's how you designate reactive power. I've got 17.44 watts of power that are lost to power factor. That gives me a total available to radiate of only 44.46 watts. Pretty pathetic. All right. So what's the solution to this? The solution is I come in here and get rid of this reactive component in my complex number. And I'm going to do that with a tuned stub, and I'm going to use this Smith chart to design the tuned stub. But all it's going to do is change it from 32.5 minus J30 to 32.5 minus J0. So what I did was, this one's a little harder to see. I guess I'll go ahead and blow it up. What I did was, I changed the direction on this. And I started out with 32 minus J0. So now if you look over here, you see my line drawn right up the resistance side. It's going to hit both of these circles, these wavelength graphs at 0.0 because it's all resistive. That's what I'm after, strictly resistive. Now I know that I've got 0.282 of wavelength, 0.282 wavelengths of coax that I've got to go around. But now I'm starting at the load. So I want to get on the toward the generator scale and go over to 0.282 on the toward generator scale. So I'm going all the way around here to this point, 0.282. And then I'm going to draw a line from that point through to prime 0. then the next thing I'm going to do is I'm going to start out with my first, since I've marked this off, my red 0, I've got, I think it's 0.65 plus J0 normalized impedance. Then I draw this inner circle with my compass. I'm sorry, I guess it's 0.62, something like that. And then I'm going to go down here, and I'm going to take this same radius, and I'm going to mark off the SWR, and I'm going to mark off the step attenuation point. Notice that the SWR is somewhat lower than it was. It's like 1.76, 1.78, somewhere in that neighborhood. So then my step attenuation shows up over here somewhere in the neighborhood of 6-ish. I'm going to now take that 1 dB of known, not the 1.3 dB, it's going to be different this time. I'm going to take that 1 dB of impedance or attenuation in my line, and I'm going to move towards the generator 1 dB, which would put us in this point right here. Then I'm going to take and measure off the new radius with my compass, and I'm going to draw another circle here. And notice they're a little closer together, and this gives me my new corrected at the radio SWR and impedance. All right. So the SWR at the load now is 1.85. The SWR at the generator or the radio is 1.78. They're really not terribly different, are they? The impedance at the generator is 80 minus J17.5, or in plain English, 81.9 ohms resistance at a minus 12.3 degrees phase angle. So the standing wave loss coefficient of 1.16 for a total feed line loss now of 1.16 dB. Cosine of 12.3 degrees is 0.977. So that means of 100 watts output from the radio, 97.7 watts is real power. What's left is reactive power, because there just isn't very much reactance in the circuit. There's just a little bit of reactance left over from the coax itself. So if I do a comparison now of before I put the stub up and after, the before I had 27 watts of feed line loss. Now I've only got 23.4 watts. And you say, yeah, great, big deal. It's not really that much. You're right, it's not. Reflected power, I was reflecting 11.3 watts before. Now I'm only reflecting 8.9 watts. Okay, it's a couple of watts. We ain't setting the world on fire. But look at the power factor loss. Kind of different, isn't it? The total power being delivered to the antenna. Now, I still don't have the antenna's efficiency involved. This is just the delivery efficiency. The total power being delivered to the antenna before was 44.3 watts. Now it's 65.4 watts. And don't tell me that it won't make a difference. And all I had to do was cut a piece of coax. But I gotta have Smith chart to figure out how to design that, where to put that piece of coax. Is it in series? or is it in parallel? Is it shorted or is it open-ended? And how long is it? All right. What I wanted to do was show you some more slides that were from these I got off of a Smith chart software program called Transmission Line Details, and I just wanted to show a few things on them. So this particular one, it shows match line loss in dB per 100 feet for Dave Martin's favorite 450 ohm window line. And notice this is dB over here, and even at 800 megahertz, it only has 1 dB of loss per 100 feet. So everybody should be jumping up and saying, let's go get window line. Well, maybe. Remember Bud's first law of antennas. If it's an antenna, it's a compromise. So Dave's made a compromise here that makes a lot of sense for what he's doing. One of those compromises is he trades off some noise for efficiency, and in his case, the way his antennas end up designed with that, the window line very easily becomes a part of his tuned antenna. So it makes it easy for him to say, okay, a little bit of math for this frequency, I need to add 6 feet of window line in series, and that'll tune my antenna. It's a trade-off. Some things that are negative with the window line. One, you can't tape it to the pipe, to the tower going up. You got to put standoffs on it. You got to stand it off away from those things. You can't bury it in the ground like you can coax. And it is more susceptible to urban noise than coax is. So you just have to consider what are the things that are important to me for this job, and what are the things that are not important to me. If efficiency is important to you, this window line is something to seriously consider. Here is the true impedance, characteristic impedance based on frequency. Again, this is megahertz here at the bottom. This one really doesn't change very much, but it does go approximately 1.5 dB difference in characteristic impedance. That's not really enough to amount to hell of beans to worry about, but if you wanted to get an anal like I am, you could calculate around that. And notice also that the velocity factor on this is very high. So it electrically travels further in a shorter piece of transmission line. But another thing that's important to note is that the change in velocity factor is very small compared to my favorite, which is the LMR 400 Ultraflex. And you'll notice here that at 100 megahertz, it's 1.5 dB per 100 foot of loss. That's a good bit. At 30 megahertz, it's approximately 8 dB, 0.8 dB of loss per 100 feet. So the losses are a lot higher. Now, down here at the bottom of this little graph, notice it shows a 0.85 nominal velocity factor. This K0 is the copper resistive losses. This K1 is the losses due to skin effect, and K2 is the losses due to the dielectric. With a total loss at this frequency here of 0.806 dB per 100 feet. Here's his changing characteristic impedance based on frequency, and notice it changes somewhat more than the window line does. And here's the true velocity factor at frequency. And this is part of the challenge with these off-center fed antennas is that as the frequency changes on the coax, the feed point on the coax is actually changing. It's moving because of the change in the electrical length of that coax at the different frequencies. And I've just got a few more in here. Let's see, this one is LMR 240. That's RG8X. Notice that the losses on it are a lot higher. So at 30 megahertz, it's losing 1.5 dB per 100 feet, a little over that. At 100 megahertz, it's almost 3 dB per 100 feet. So if you were going to run your 2-meter rig at 144 megahertz, you would be talking about less than half of the power coming out of your radio getting past the losses in the coax. Got to keep that in mind. Here's the characteristic impedance, and it changes quite a bit. It changes over, well, let's see, I got roughly almost 2.25 ohms of characteristic impedance change over the length of the graph. And here's the true velocity factor. It's changing a lot too. So at 3.5 megahertz, it's 0.82. At 30 megahertz, it's 0.833. That can be different. It's important to know what this is if you're going to use the chart. Excuse me. It's important to get this as accurately as you can if you're going to use a Smith chart to design the stub for correcting your SWR. I stopped here deliberately today for a couple of reasons, but one of them was this calculation of stubs, if you will, is going to require some familiarity with admittance, conductance, and susceptance. And essentially those are the inverse of resistance. The inverse of resistance is conductance. So 1 over R equals G. 1 over impedance equals susceptance. And 1 over I'm sorry, I got that wrong. Susceptance is 1 over the reactance, 1 over the resistance, or 1 over the impedance is the admittance. Anyway, we'll need to go through that some and give you guys a little, just a little bit of familiarity with working with that, and then we'll figure out how to use the Smith chart to design a stub or something of that nature to improve our SWR at the antenna itself. Doesn't really do us a whole lot of good to improve the SWR at the radio, although I admit that it will do some good. But if you've got a big reactive number anywhere in there, you're not getting very much out of an awful lot of power you're putting out of your radio, because the only power that radiates is real power. And the bigger that phase angle gets, the less real power you've got coming out of the radio. So, any questions?
I do have a question. When you make your stub to adjust the antenna, and you say now there's more power going to the load, is it radiating out that stub, or is that just the electrical?
It's not radiating out the stub. Now that might depend a little bit on how you design the stub, but no, the stub is basically acting as a matching transformer.
So I guess the question more theoretical, but is that 65 watts or whatever, is that being radiated, or is that just being it's between the antenna and the stub?
It's between the that's what's getting to the antenna feed point.
Right.
There are still issues in the antenna as far the antenna has its own efficiency. So if I put 65 watts into the antenna and I'm only able to radiate 32 watts, then I've got roughly 50% efficiency in the antenna itself. So there are issues in the antenna. For instance, the antenna has copper resistance. We call it I²R losses. So there's current flowing on that copper wire. The bigger that wire is, the less resistance there is, the more efficient it will be. Keep that in mind. You may have a balun there. If the balun is a low power balun, like 200 watts, then the wire is probably pretty small. The smaller the wire, the higher the resistance, the more the losses, the lower the efficiency. You are probably going to have some on anything other than a dipole or a balanced dipole-like radiator. On anything other than that, you're probably going to have some ground losses that you have to deal with. There'll be losses on the dipole or any other antenna as it couples to the ground. We don't want it coupling to the ground, but it's going to. There may be some losses because the antenna is too close to the ground. When all's said and done, I'll bet you take 90% of the ham radio operators' antennas around here, and I'll bet they're well below 10% efficiency for the total system. Somebody tells me he's got a 90% efficient antenna, I'm just going to take that with a grain of salt. It ain't likely.
Yeah.
The other thing that I would like to point out to everyone is there's a program that you can download this thing off of the ARRL website, and it's called Transmission Line for Windows, or TLW. It was written by Ham. The copyright is owned by ARRL. It's free. It also comes on a CD with all kinds of great information on it when you buy the ARRL antenna book. And there's other things besides that on there. One called TL Details. Got even more information than Transmission Line for Windows. I thought I heard somebody else back there trying to break in before I got rude. Somebody want to say something? Is everybody else muted, Mike?
No, that was me, Bud, trying to change streams.
Oh, okay. You have a comment?
No, other than thank you very much. I'm still digesting a lot of that, but it's one of those things you're going to have to go through my thick skull a couple of times before it sinks.
Oh, man, I'm telling you, I resemble that remark. The reason why I was asking you, Dave, about if you had any specs or something specific on your window line was because what I wanted to do was to get you a process where you could see, you were telling me when I visited your shack that you could stick a piece of that window line in the area and tune your antenna. Well, one of the things I'm about here is giving you a little tool that says put 7 feet 2 inches in there to tune to this frequency. So, and I think we're going to be able to do that with the Smith chart program and that transmission line for Windows. And I think the last time we did this, I'd also showed you that TLW software and where it would actually design an L or a pi type matching device for you.
Yeah.
But it'd be a lot easier if you're out on a Mars deployment. Say, okay, I just need 6.5 feet of window line.